congrats to those of you who are here. And we're going to start our morning session hearing about thermal energy reservoirs in the ICM at high redshifts.
Okay, thanks. Good morning, everyone. My name is Dazhi Zhou. I'm a PhD student at the University of British Columbia. First, I want to thank the organizers for giving me the opportunities to present my work. So in this talk, I will talk about a large thermal energy reservoir in a nascent intracluster median at redshift 4.3. So you might wonder, so the intracluster median is usually the probe of the cosmology. How can it relevant to the galaxy evolution? So I will try to convince you the intracluster medians is interesting and pretty crucial to understand the galaxy evolutions. So a little bit background. So intracluster medians is hot plasma in galaxy clusters. They are pretty abundant, pretty hot, and we also have the self-similarities for the intracluster median, which means the ICM profile is roughly independent of the mass or ratio of the galaxy clusters, but this is only for the relaxed clusters. And it also have very huge impact on galaxy evolution. It's usually pretty tightly connected to the influence of the environmental impact. So one of the ways ram pressure stripping, so the cold gas in the galaxy can be stripped away because of the intracluster median, and it will also cause the galaxy of the environmental quenching. And because it also radiates the strong X-ray, and we can also see the cooling flow that the ICM can cool down and also be accretive to the galaxy for the further star formations. How can we detect the ICM? So the first way is for the X-ray emissions, but I want to strengthen another kind of the probe of the Ziyagin-Zeldovich effect. So there are two different probes. One is a kinetic SZ, another is a thermal. So as you can see here, they are pretty different spectrum feature for the KSZ and the TSZ. Especially for the TSZ, you will expect for decrements. It's because that the ICM will have the incompetence scattering, inverse competence scattering to make the dust continue of the CMB spectrum shifted to a higher shorter wavelengths. So SZ is very crucial to test the feedback models, especially for the baryonic feedback. So as we show here, so this is the model predictions from a various of different cosmological simulation with different feedback models. You can see with different feedback, we expect a totally different KSZ power spectrum. So we can use it to constrain the AGN feedback. Another is the thermal SZ. One of the key features is the universal NY relation. So your SZ strength, the thermal SZ strength, is tightly correlates with the cluster mass. But at higher redshift, we might not expect such a tight NY relation because we have a smaller halos, and the baryonic feedback process can influence your intercluster median more easily. So one of the unique features of the thermal SZ effect is it won't be weaker at higher redshift because of the self-similar evolutions. It is mainly because of the hydrostatic equilibriums of the intercluster medians, because we have the cosmic ratio evolutions of the cosmic critical gas density. So at higher redshift, we usually expect higher pressures for the ICM. And so this leads to one of the results. For the relaxed clusters with the same halo mass, the TSZ signal should be stronger at higher redshift. But there are also some challenge for detecting the TSZ signal at early universe. One is because of the thermal histories of the gas. We expect the gas should be cooler in the early universe, and we also expect the halo mass should be smaller once you go to the higher redshift. Another problem is because of the obscure star formation rates at higher redshift. It is much higher, and it will strongly contaminate your TSZ signal. So today there are only 3 systems with TSZ detection at redshift around 2. So in this work, we're trying to have a case study of the protocluster SPT2349. It is a very massive halo at ratio 4.3. There are like around 30 galaxies within 200 kiloparsecs regions, and the integrated star formation rate for this small region is around 500 solar mass per year. In the earlier work, we discovered that from the low resolution observation, we discovered that the cold molecular gas are much higher than the high resolution observation, which suggests that a substantial cold molecular gas are not associated with the individual galaxy, so it can be a hint of the preheated proto-intracluster medians. And in this work, we also noticed the fact that in the low resolution observations, we have the long wavelengths continue lower than the total flux density at higher resolution observation. It is also a hint of the TSZ contaminations. So we have very deep ALMA data. It's around 20 hours. And after we subtract the dust continuous source from the Fourier space, we found the TSZ signal around minus 160 microjansky, and it is about 10 sigma detections. And for such thermal SZ detections, the signal requires 10^61 ergs for the thermal energy. So this really suggests that there is a very huge, large thermal energy reservoir in these protocluster systems. So it is very hot, and how we know it is hotter than we expected? Well, we can place it in the universal MY relations. So this plot, we compare a series of the low Z and the mid redshift with TSZ detections, and this one is the TSZ detection of the 2349. As you can see, for the low Z, it is very consistent with the MY relation, but for the SPT2349, it is about 5 times higher than the MY relation. And we also notice that for the literature, like the ratio around 2 TSZ detections, it is slightly below the universal relation. So we just want to get rid of the dependency of the cluster mass so that we factor out the cluster mass and trying to investigate its ratio evolutions. Interestingly, we can see that for the ratio around 2 cluster systems, we usually have the TSZ signal below the expectation from the self-similar evolutions. But for the SPT2349, it is way higher than the expectation for the ICM, which suggests that the self-similar evolution might be broken at some point. So we also investigate the simulation predictions. So we try to check the ICM in the TNG cluster simulations. But surprisingly, we found that the TSZ signal is quite consistent with the expectation from the self-similar evolution track. So this is like something that very surprised me. So what happened here? So we also investigate the MY relation at ratio about 4 in TNG cluster. We can see that the MY relation is already pretty tight at such an early epoch, so which suggests that your hot gas is already in the hydrostatic equilibrium. So we also have a kind of video to illustrate that. So here is a simulation of the SPT2349. As you can see, once your gas has been heated, it will just quickly expand and to lose the energy to keep it to be in the hydrostatic equilibrium. Yes. So, and then how can we understand the strong TSZ signal in the SPT2349? So we think the most natural explanation is the large-scale heating from the AGN. As we know, the radial mode of the AGN feedback is poorly understood, and it's like the prescription in the simulation are pretty empirical, and it's like pretty different throughout the different simulations. And in 2349, we have 4 radial AGNs in the system, and Scott will talk about this later for details. And we also calculate the total energy output from this system, including the star formation, the X-ray AGN, and the radio AGN. And the total energy output is comparable to the energy required by the thermal SZ signal, and which suggests that we need very tighter energy coupling to make the energy stored in the intercluster medium. And another interesting finding is that the radio AGN can contribute like over the 80% of the energy, which suggests that it is a dominant source of the heated ICM. And we speculate that the dense ambient gas at such a high ratio in such a dense structure might prevent the expansion to suppress the work done by the PDV, so that you can have more work energy to be stored in the overpressured ICM. So some kind of the implications, we think like the ARMA will be the answer as the next generation tools to have the high ratio of TSZ service, because the halo is more compact at higher ratio, so it is not suitable for the single dish low resolution telescope have efficient detections. And the ARMA, we have very high resolution, and this scale is kind of very ideal to detect the thermal SZ at higher ratio, and it can be reachable. And we also have a sample of the different systems, which are also similar to the SPT 2349. If we want to see whether the self-similarity holds at such a high ratio, or so the SPT 2349 represents a crucial stage for cluster formation, so that you have overheated ICM. So we can explore the TSZ signal in other systems, such as the distant record and other SPT pro cluster samples. So we predict that only 10 to 20 hours ARMA observation time is required to verify if the self-similarity exists for the ICM at such an early epoch. So I will leave my summary slides here, and I will also point out that I will be on the job market soon, and I'm happy to take any questions.
Thank you. Questions? I've got one. Do we worry at these, from the observational side, and I'm naive enough that I don't even know which way it would go, but do you worry that given the resolution and that the SZ is contaminated by the radio galaxies potentially at these frequencies?
That's a very good point. So that's the advantage of ARMA. ARMA is interferometer observations. So you have your signal at different scales, which means, maybe I can go back to the previous slides. So you can see in our system, we have like over 10 very dusty galaxies which present the positive emissions that can contaminate the TSZ effect. But the interferometer resolution observation can be treated as Fourier filters that can help you to filter out the high frequency signal, so that you can have the extended low frequency signal left after you do such a filtering process.
So,
Thank you.
share your screen and get ready to do it.
Other questions? We've got time for maybe one or two more.
Right.
No, just
Maybe we can have Scott come up and we'll start setting up.
Okay.
oh, sorry.
Energy there, but we heard from Renew yesterday about injecting the radio AGN energy over time,
Yeah.
accumulation of the energy. So I was wondering, whether you can say anything about this, the period that you have to inject those energies. And how
Yes.
you can,
So we have a pretty idealized calculation, like probably it's only approximately true for the first order, in the first order. So we assume that the radio AGN and the star formation and the X-ray AGN have the lifetime of 100 million years, so that we use that to to calculate the total energies injections from these energy sources. And it just provides us comparable energies.
You think that a single episode of radio agent injection is sufficient? Is
I
that
think
your
so.
conclusion?
It is mainly because of our because of the in simulations we already find that the cluster will be back to the hydrostatic equilibrium very quickly. It is because at higher ratio we have denser gas, so that your relaxation times will be shorter. So we don't think like in the previous episodes you can have any energy stored in the current time.
All right. Why don't we thank Dazhi one more time, and next up we'll have Scott Chapman continuing our discussion.